Good morning, everyone. Assuming you are in Brisbane or Queensland, and good afternoon, good evening, anyone else. My name is Yusri Muhammad. I work as a lead consultant at Telstra Purple, and I'm here today to talk to you about some of the tips and tricks for building robust big data applications, developing them, deploying them, and operating them. And just for the sake of the time, I will not talk too much about myself or whatever, but I'll start a little bit of journey, my professional journey here in Australia. So I started with Redify a few years ago, and then Redify has been acquired as a Telstra company. Just giving you an idea about how I had the chance to work with big data applications. Then eventually there was a rebranding inside Telstra, and we have an entity or a brand now called Telstra Purple. And as you might expect at Telstra, we have lots of big data assets and big data applications. So hence you will find the yellow elephant, which is kind of a visual indicator of big data, the Hadoop kind of ecosystem. All right, so a little bit of history, not around myself, but around Hadoop itself or the big data ecosystem. So everything started around 1998 with Google. So Google wanted to index the internet, which involves processing huge amounts of data. And then eventually they invented MapReduce as a new computation algorithm or paradigm to handle big data. And then based on that, this kind of inventions and requirements, Hadoop ecosystem has been introduced. This is a V1 thing. It was like what at that time it was pretty cool or amazing, but according to the standards of today, it was very slow and cumbersome. And then this was a new resource manager because Hadoop was originally slow and having problems with resource allocation because it's a distributed environment. And then to make things much more fast and user-friendly, some people at, I think, UC Berkeley introduced Spark so that lots of computation can be done in memory and fast. And also many people with SQL skills like SQL DBAs, administrators, or business analysts, or anyone really with a SQL skill can use Spark. And just recently, a few months ago, they have introduced version 3, which is about lots of new features in the platform itself, stuff like Delta Lake, and also allowing Spark to run on environments like Kubernetes. So yeah, this is the latest and greatest stuff from the big data community. So the agenda for today is kind of 6 major tips. We'll start with every one of them with like an individual demo. So we'll start with a bit about your data and the storage format for big data applications, and then we'll see what will be the impact of certain underlying file systems, and we'll see how big data applications are kind of designed to be balanced so that there will be little skewness. We'll have a look on the QA of big data applications and how things can be done in that aspect. And we'll wrap up with a bit on governance, lineage, security, and stuff like that. And finally, some ideas around the tooling and how could it help in your daily workload. So let's start first with your storage and data. So big data is normally about, when someone talks about big data, he will usually mentions the 4 V's or 5 V's or whatever. I mean, so, and the first V will be volume for sure. Okay, so big data applications, mostly we store our data as blobs or files on some sort of a file system, a cloud file system or on-premises file system. And you need to understand if there's a proper HDFS file system or Hadoop distributed file system, or it is something like a blob storage or a blob store or object store like Azure Blob Storage, and that might make a difference. Plus, for sure, the idea is that most of these big data applications, we store data in 2 common data formats. One of them is called Parquet, and the other one is called ORC or ORC. And then you need to understand the scheme of your data sets, what type of columns you have. Is it like what plain columns like integers, float, and stuff? or you have arrays or more sophisticated or nested data types. And then you'll need to assess your data, have a look on it, and see if your data can be compressed more or stored in a little bit less size, so that your subsequent pipelines will run fast and efficient. Because it's not about storing as much data as you can, it's about storing them in an efficient fashion, so that the whole pipeline will be fast and quick. So let's go to the demo here. I switch to, sorry, too many windows, VS Code, and our first demo will be about how your the scheme of your data and how certain columns are stored will make a difference. Okay, so what I have here, actually, because this kind of demo takes like some of the steps take a few minutes to execute, so I've run the script, but I'll show you the ideas step by step. So what we are going to do now is to create a small table, an ORC file. Think about it like an Excel table or something like that. And at every step, we'll add or update the data type of a certain column, and then check the size of the outcome data set. All right. So here is the first step. This is like what Spark code running on my Windows subsystem for Linux virtual machine or something. So you just run the Spark shell, and this kind of statements, you can run them in the shell. And by the way, I leave a link to all the demos and the source code in the chat shortly or later after we are done. So I think if anyone, I'm not sure if you can see my, just asking if people can see, where is that? My Visual Studio Code.
Right now we can see your Chrome. So
no, I mean for now, can you see my Visual Studio Code?
Yes.
Okay, very good. Just in case. All right. So first statement here is about creating a data frame, 10 million rows, I think. Okay, and then storing it at a certain place on disk. Okay, and then with every step, we'll be showing the a subset of the data or the first 5 records or something. All right, so 10 million data set stored as ORC file on disk with a single column, which is just a sequence number, is around 200 kilobytes. All right, let's think about adding a string column. Okay, so the next step is to add a string column. It will be a prefix and some random number in the range of million. So we have like what 10 million unique, random combinations of that string. So you can see here that we still have the sequential integer, and then we have a string column and lots of random numbers here. So we have lots of unique combinations. So eventually, when we add this kind of string column, our data set size will jump to 71 megabytes. I hope you can see that. Okay. So if you like to dig deeper into the documentation of such storage formats like Parquet or ORC, you will identify that strings are stored as dictionaries. All right. So depending on the cardinality of your column, your data can be compressed well or not. So because the dictionary will be smaller and stuff like that. So let's assume that we'll decrease the cardinality from, you can see here the cardinality initially was kind of 1 million. Let's assume that we'll decrease the cardinality to 10 unique elements only. So we still have the string column now, but with smaller cardinality. I mean, like 10 unique combinations of the string value. All right, you can see here that now we went from 71 megabytes to 5.2, which is a great achievement. Okay, so just know that depending on the cardinality of certain columns, especially the string data type, data can be compressed better. Because yeah, this kind of columnar data formats, they're stored as columns and stuff, but they also they have built-in compression. Okay, so the next idea here, just to prove that the size of string itself does not matter actually, and the only thing that matters is the cardinality, or it doesn't virtually matter. Okay, so the next experiment here is that the same string column, but I've made the prefix and suffix too big, or almost like a double-sized text. Okay, and let's have a look on the size again, and it is almost the same actually. Okay, so this is just an evidence that, okay, if you have a string, it doesn't really matter how long the string is, as long as the cardinality is the same. Okay, so the next step, let's like what play with constant columns. Even like what integer columns, like that sequence thing or identity column, they are still compressed. But we normally know that compression, when you have constant data or things that are just repeated, compression will work better. Okay, so in this data set, we have like what one extra string column, a constant one actually, and one extra. I mean, if you can have a look, scroll down here. Yeah, there's a code for that part. Okay, line 53 here, and constant string and a constant float. And let's have a look on the size. So once we add the two extra constant columns, the size increased a little bit, but it's mainly like what a bunch of metadata here and there and this kind of things just overhead. But actually, constant columns they can be added easily without too much impact on the final size. All right, cool. So let's assume that you have in your data set some sort of a complex data type, a struct or an array or something like that. So here we'll be just adding this snippet of code, adding an array of 100 elements, and in the array itself, the cardinality of the array, it's like what 1,000 unique array instances. So I'm adding an array column here, and let's see what will be the impact on the size. So if we scroll down here, you'll see that introducing an array column, like what exploded the size to almost the range of 1 gigabyte now. I mean, approaching 1 gigabyte. Okay, so just know that if you have arrays or nested data types or these kind of things, you will lose lots of like what compression, or I mean, data cannot be compressed similar to stuff like strings or whatever, because I mean, it will not be stored in a dictionary or stuff like that. It will be just like what stored as is, as like what a string of bits and so on. And it depends on, I mean, the encryption algorithm, compression algorithm, or the format of the column itself. So sometimes you might really get very big data increase just due to the introduction of an array column. So what can we do with this kind of column to limit our data size a bit, or maybe greatly, especially if the cardinality of this column is small? Assume that for any reason, yeah, you have 10 million records in your data set, but eventually the unique combinations here are like what 1,000 or so. So the trick here to if you can store that column or serialize it as a string using any kind of approach like comma separated values, or serialize it as a base 64 or something like that, or JSON or whatever. So the next step here, I'll take that string, array column, and convert it to a comma separated values string. Okay, so originally here it was an array, if you can see the square bracket, and now, I'll store it as a string, a plain string. And you can see here that the size dropped from 974 megabytes to 13 megabytes, which is amazing. Actually, it's kind of 2 orders of magnitude. I know this is a synthetic data set, but eventually, I mean, or practically what we had in terrestrial is something like what a daily data set of 300 gigabytes. And with a combination of such ideas here in this kind of demo script, we have like what decrease the size, the daily size, from 300 gigabytes to less than 30, which is an order of magnitude, which is also like what improved the performance and the speed of lots of subsequent jobs in the big data pipeline. So eventually, if you can store your data in an efficient way, I know there will be a little bit of deserialization if you'd like to use that array column and stuff like that, but it's a very minor computation cost that you can pay for going from 900 megabytes to 13 megabytes. So these are just like what a glimpse about some ideas around how to store data and how to optimize your storage. So eventually, yeah, you will pay less for storage in case that matters to you, and other jobs that will depend on such data set will run much faster because I/O. Okay. So I think this was a the first step about storage and columnar data format. And this is something around some key takeaways here: cardinality and knowing your data types and stuff like that. Just wrapping up most of the ideas in that Scala script. Let's go to the next idea here, which is about your file system. Sometimes you might have, I don't know, a bit slow file system due to whatever reason. The name node itself could be, on your Hadoop cluster, could be slow, or it's an object store system. So enumerating folders and digging deeper into folders will be slow. So you need to identify also what are your access methods. I mean, do you access, for example, if you are having an application, a plain application on your Windows machine or Linux machine or whatever, you can access a certain piece of data using c/blah, or you can have a network share format or something like that. And there is a difference between such access methods. And then sometimes you might need to add a little bit metadata to your big data applications to make things fast, and we'll have a look on that now. So, because metadata is something like what when you are running a SQL query on SQL Server or Oracle or whatever, and the query is slow, the first thing you might think about is, okay, let's add an index. And an index is also a metadata thing, something like what we are going to do today. So, back to VS Code. And we'll go to the next thing. So in most big data applications, data is stored in this kind of format. I mean, partitioned by some sort of a dimension, like a date or department or whatever. So you'll find some data here, partitioned by year and month and day and so on. Okay, so what we have here, let me just go to that location and fire Spark shell. I have a small data set here, partitioned using year, month, day, and it is stored twice. Once on, let me have a look here, on my Linux file system, and once on my Windows file system, and I can access both from my Linux machine. Okay, so let me give you an idea about the difference in access or speed. So I'll do this command, which will list the sizes of folders from the Linux file system. You can feel it is very fast here. But from the same WSL version machine, I'll hit the same data. It is another copy of the same data, but now it's stored or accessed on my, mounted C drive on the Windows machine. I think you can feel the difference. Okay, so yeah, depends on where your data lives. Your access to the file system itself could take some time, especially related to enumerating files and folders and stuff like that. Okay, so I'll go back to my Spark shell here, and I'll run some queries that is loading data from the Linux copy, just doing a plain filter using the year and month and day, grabbing a week of data. I got some sort of bootstrapping stuff initially in Spark, but this query actually is pretty fast. Okay, and if I try to do the same query against my Windows copy, you will feel that it will take a few seconds. Even if I repeat it again, I just don't want to waste your time. But this query, although it is doing the, accessing the same data, but data is stored in a different file system, kind of, or accessed from a different file system. So the query will take much longer. And if we switch to Spark log here, or Spark console or history server, you will notice that, this is the first run of the statement, from the Linux file system, and there's the same run from Linux file system. The other run from the Windows file system, it appears to be quite fast as well, but that was not the case. There will be some hidden work done by Spark behind the scenes, which is to just go find folders here and there and enumerate them and find where the data is to be retrieved. Okay, and it is a bit misleading that this kind of thing sometimes it doesn't appear here on a Spark. So you might think that your jobs are fast, but they're not actually fast. So to handle such problems, especially on slow file system, which is my Mount C drive here. We have two kind of tricks. The first one is to try with some Spark API to provide the base path, and then specifically mention the folders you would like to grab the files from, or your data from. So I know I need the first week of October 2019, so I'll put this path, and then I provide an array of strings. Every one of them will contain one folder. And then I'll put paste here to paste these couple statements and run, and you can see it was very fast. We got the same result, and it executed quickly. So if you'd like to do it this way, that would be totally fine. But I think this is a little bit clunky and not very easy to use in most situations. So the other approach, like what I've mentioned related to speeding up normal SQL queries or whatever, is to add metadata. And the metadata that we can introduce here is to use a tool called Hive. So think about Hive like providing an extra abstraction layer on top of this file system things. So it can tell, okay, if I'd like to go grab first week of October 2019, I'll need to go into these specific folders directly. I don't need to go and list folders and do searches or whatever. So I'll create an external table thing, which is just a layer on top of the data. It is not the data itself. The data is still stored into my Windows file system. So I'll just create an external table on top of that, and I'll instruct Hive to partition, or inform it that the data is partitioned by year, month, day. So I'll grab this thing. This just to create the metadata. It will take a few seconds to build the metadata for the table and so on. But eventually, if we hit the same, or run the same kind of query, but now not against the plain file system location, but actually against a Spark table, I'll grab the same query, assuming Hive is helpful and done. Okay, we're done. Grab the same query, hit it quickly. Yeah. So that's it. So sometimes you might need to think about your underlying file system. Does it take too much time to enumerate folders and stuff like that? And do you need to have another layer of abstraction or indexing or whatever to make your queries run fast? So this is just an idea or a glimpse about what would be the impact of different file systems on your big data pipelines. Let's go to the next one. So the next one, pandemic time. I'm not sure if everyone is going back to the gym now or what, but normally when you go to the gym and pick a couple dumbbells, probably you will pick dumbbells with the same weight. It will be very unusual to pick 10 kilograms here and 20 on the other hand. Does it make sense? So the same applies for big data applications. You need to distribute your compute load as fair as possible across all the nodes you have on the cluster. And the same applies for the storage. It's not so good to have your data set stored as 20 files, where 19 of those 20 files are very small files and one file is a very big file, because big data is normally done over distributed infrastructure, and every node on the cluster will pick one of the files or two of the files or something like that to process. And if the files are not already of similar size, some of the nodes will be heavily loaded or something like that. So generally speaking, it's also always recommended to have your applications work in a balanced and fair fashion. All right, let me give you an idea about what I'm talking about here, because seeing is believing instead of just talking concepts. So let's move to skewness ideas. So I think I still have the same Spark stuff running, so I can come here. But actually, I'll kill this one because I'd like to start with a fresh shell, because I'd like to show the stuff in the console simply without confusion. So what we have here, until the shell is ready, I have a small data set containing some sort of geographical information. All right, it's not very huge. I don't remember, a few hundred megabytes or something like that. And then let me just load this dataset and show the first few records. Okay, it's a simple table, some geographical information about Queensland or places and stuff like that. Then in most, or actually in the MapReduce itself, the idea of MapReduce is to go pick some data, filter it, do something with the filtered data, and then store it to disk or stuff like that. And the same applies here. Many queries will start with loading data and then doing a filter and then maybe doing some sort of transformation or mapping, and then eventually storing to disk. So what I'm doing here, I'll filter the data for a certain city here in Queensland, and then like what store data to disk. But we have different APIs for storing data to disk, because you have an option to control how many files are generated. Because big data is done over distributed infrastructure, so you have multiple nodes running in parallel, and every one of them is generating a piece of the outcome. So you don't have a single final file outcome. All right, I'll take this one and run it, and I'd like you to notice what will appear now in the console. So there's something called the coalesce, which will take the data and store it in 4 files. You can see here, there is a 4 here, if you can notice. So this kind of 4 means like what this query in this API, it has a bad side effect that it will limit the number of threads running or servicing this job or query to 4, which is not good, especially if you have lots of compute and a heavy or complicated query. So this one finished, it's not a big deal, but if your query was like much heavier, that would be a big problem. There is a similar API called Partitioned, and just to let you know, I have 12 cores on my laptop, and have a look here. You have 12 here, meaning Spark is like creating 12 threads to run this query. All right. So if we go now, just to give an idea about why this matters, I refresh the screen now. So the first one was the show one for displaying the data. This one was like choosing the coalesce API. It took 5 seconds. Okay. The other one was like doing using the different API repartition, and it took 3 seconds. Like maybe two times faster or whatever. But actually, if you try this against a real big data set, the difference will be very, very radical. Okay. And you can imagine here from this kind of thing, the first query was running against like 4 threads only, and or actually this kind of how much parallelism Spark is doing to run your job. And this one is like 12 jobs to do the filtering or something like that, and then 4 additional jobs to do the persistence of data on disk, hence the 16. So if you even don't care about the speed or whatever here, let's have a look at the final data. Skewness. So this is the data from the first API, coalesce. And you can see here that, yeah, like data size is not very consistent. Some files could be small, some files could be a bit large, all right, which is not so good. But if we go to data repartitioned, the other API thing, they are producing effectively the data is equivalent. I mean, they are pretty identical. But the file size is here. Look at this one. This is very, very balanced data set. Okay, so I mean, using the correct API, just you need to consider what APIs you are using and whether they are like providing or having the what is that? Doing the needed parallelism and not keeping your jobs very slow. You might have like 100 cores available, but your job for whatever reason could be using only 4 out of them. And for sure, you need to consider making your final files or your output data balanced. All right. So this is about gem and balance. So next thing, I hope this is not related to COVID, but yeah, it's more about data quality. In big data applications, we always use the classic things like all other types of applications. still unit tests and integration tests are useful and recommended. But because big data applications normally run as like background jobs or batch jobs or even streaming or whatever, and you don't usually have a screen open in front of you to play with the application and see like a normal web application or whatever, things most of the time run in the background, and you better know or like put some measures to test that the quality of your outcomes or whatever produced from your jobs or processes is good, because otherwise there could be problems and you will be in the background. No one would know until it's a surprise, and probably it will not be a good surprise. And you will also need to think about notification and diagnostics. So think about it. You better put some like logic at the end of your jobs, or maybe at the beginning as well, to check if the input data is good or not. And more importantly, at the end of your jobs, make sure that the final outcome of your big data application is good and it makes sense. And if there's a problem, you can like leave some logs and diagnostics, and maybe also do some notifications so someone will take action fast or quickly. All right, so I'll go quickly through this one because, yeah, for the sake of time. So what we have here, sorry, what is that? Okay, I'll exit this one. And I'll be using a library from AWS called DQ, which is providing some sort of declarative data checks against your data. So what we have here, let me show you a small thing. So I'm joining some data from two CSV files, one of them containing some customer orders, one of them containing some country information. So we have country, there's a country table, there's an order table containing a country code, and I'd like to join them to have a final data set containing all the information about orders and continent and region and stuff. And this is the joined data set, okay? So I'd expect that this data set, it should have a unique order ID, and cell amount should be always positive and doesn't contain null and stuff like that. And if any one of these kind of constraints fail, there should be a problem. I mean, I can fail the job or send a notification or whatever. So this is what we are talking about here. Just implement, grab some library, doing some sort of declarative checks against your data, so you can provide it with a data frame and tell it to apply some certain checks, data quality verifications, a certain column is unique or complete or whatever. So I'll just define this function. Okay, it is defined, and then I can run this function against my data set, which is the orders with country information, and it can tell me like if it is okay or not. And if it is not okay, you can dig deeper into problems. I mean, it can tell you what column has a problem or what kind of condition failed. All right, so let me show you a simulation about when you are doing unit tests, you always prefer to test the failed condition and the successful condition and so on. Yeah, red and green stuff. Anyway, so I'll fake a duplicate country table, because sometimes some of these kind of data sets are owned and operated by other teams, and you don't have control on such data sets. Sometimes you have rubbish data in, and you'd like to guard against that. So I'll simulate a duplicate country table. So eventually, our final table here, you can see that you have two records for the same order, because eventually we had in the country table we had two records for the same country, which is bad. Okay, so let's apply the same thing, and I can imagine you understand, or you are guessing what will happen now. So we'll get an error. So based on this kind of check, I mean, you can grab that status and implement some logic in your application to fail the job, send a notification, do something about it, or at least leave some traces in your logs or whatever about what's happening in your applications, because that would be very useful for later troubleshooting and diagnostics. All right, very good. So that's it about quality. It's normal kind of advice: garbage in, garbage out. All right, cool. nearly there. So what's the next thing? Governance. All right, so the boring stuff here. So most of us will not be very excited about doing such things, but eventually when your big data cluster grows and you have heaps of data sets and jobs and processes running here and there, it would take more than an Excel sheet to handle all this chaos. So eventually you will need to have an asset catalog. You'd like to have some tool to help you I'd like to go and find a certain data set that was generated last year before we had a certain partnership with a client or stuff like that. So an asset catalog is very important. Plus for your all or most of your critical data pipelines, you'd like to have a lineage. So you'd like to understand if a certain data set is produced, what were the input data sets, or if there is an input data set with or a certain kind of data set identified to have a problem, what were the impacted other outcomes or applications or whatever. So lineage is very also critical. Plus, you'd like to have some sort of classification and tagging thing, because things like what we have lots of data sets. Is it some of them could be financial or confidential, or they contain PII information or cannot be shared with external clients or whatever. So yeah, you need to have some sort of automated tool to apply the tagging on that asset catalog. Plus the integration of all these kind of three bullet points of the catalog and lineage and classification will also contribute to security. You'd like to handle security in a more smart way. So if a data set is tagged as confidential, it can be, a certain security tool like Apache Ranger can be used to automatically set correct role-based permissions. So you don't need to go and remember and do things manually here and there, and eventually you will forget to do things. Okay, so let's have a look on lineage, or actually governance. So the most important tool, or maybe the most common tool for doing governance with Hadoop is called Apache Atlas, and it can integrate with Hive and Spark and many other big data applications. Where is that? So what I have here, I run a very similar query, joining orders and countries and producing a certain data set. But I'd like to have this kind of job, a very simple job, in a more kind of managed way, and data sets should be tracked, and there should be a lineage, and we'll have classification and so on. So let me give an idea here. I'll switch now to a Docker container containing Spark plus Atlas. All right. So here is my container containing the CSV file for the input data we have, plus my demo script, which is very, very basic thing, reading some CSV, doing a join, and writing data to disk. Nothing magic here, except for when we trigger the script, we have a bit of integration with Atlas itself using some kind of Spark magic and an open source library from Databricks called the Spark Atlas connector. So paste, run this stuff and hope for the best. Okay. It will take a few seconds, but I just want to wait because, yeah. Okay, so this is the data set to be written. Yep, an order table with a bit of country information, and everything is done. So I'll switch to Atlas web console, which is hosted on that Docker container. So I log into Atlas. You can see here that you can track certain data sets. So for example, I can switch to the advanced mode, and I can track stuff. These are kind of artifact types. So we have something called FS path, which is a data set stored on a file system, on a plain file system. There is also something like HDFS path, which is a data set stored on a distributed file system. We have stuff like Hive table, Hive column, Hive database, and so on. So I think the data set was called, I hope the free text search is pretty reliable now, so I can grab this one, put it here, and you can see that, okay, I can use plain text or maybe some sort of other advanced Solr-based SOLR in case You need to Google it or whatever. Free text searches to find out my data sets, and there are like lots of other advanced search features. So if I go to this one, there is a data set generated. I think there should be something about timestamps and so on, maybe. But eventually we have this is a outcome data set, and then I can come here, have a look on the lineage, and then I know that okay, this data set came from the orders and the countries through an application, a Spark application called Bootcamp application. This kind of things can have like what timestamps and so on, or whatever, or versioning. But eventually I know means the origin of this, just like what, because this week was state of origin and I'm still excited about it. Just pretending to be linked to football, although I'm a soccer fan. But yeah, so you have a lineage here, and on top of that, what else? Let's assume that we'll go to the orders data set itself. So this is the orders, and someone told me, okay, the orders data set, it contains financial information. So this data set should be tagged what financial or important or whatever. So we can create some classifications, and then you can apply a certain classification on one data set, and you can take that propagate, so that if any other data set is like what produced out of this one, the same classification will be applied as well. So I click add here. All right, cool. So I'll go and search for my, have a look here. If we come here, we'll find that we have a financial classification, but we are on the orders data set. But if I switch back to my orders enriched, which was the output data set, I can see that, yeah, the same classification has been propagated. And yes, this one is also market financial. And if there was any kind of security logic or permissions to be applied automatically, it will be applied on this one as well. And if we run the same job once again, and maybe produce the data in a different folder or whatever, the new data produced will have the same propagated classification. So this is just like what some ideas about how to use tools like Apache Atlas to help you having a catalog, an asset catalog, applying classifications, and maybe integrating with other tools like Ranger to apply security in a smart fashion. So yeah, governance does not have always to be boring and dull. All right, cool. So finally, I think almost like maybe out of time, or just like give me 2 or 3 minutes. So about tooling. So normally, the tools that come with the most of on-premises big data infrastructures are somehow boring and not very easy to use. So the idea is that our workload normally will be most of the time interactive queries, and then you can grab this kind of queries and bundle them in a jar or whatever and deploy them as a batch job. You need to have source control integration and nice diff experience, which is not the case for Jupyter notebooks a long time ago, but there are ways to handle that. And there is also options to have pipeline notebooks, so that if you have a big problem, you can divide and conquer your problem into multiple small notebooks, and then you can pipeline them together, instead of having a very 500 lines notebook, which is hard to read and hard to manage. And you would like to have a tool that will have a very good local experience. You can develop most of your stuff or proof concepts or whatever locally, like what I'm doing today in this talk. Plus, you would like to take the stuff that you have developed locally and just push it to be run on the cloud. Like Akanksha mentioned in her talk, there was this kind of Azure compute. You can have a compute cluster, so you can try with a toy data set and then push it to the cloud to run against the real big data set if needed. So I'll show you a small tool here to help with that. There are other tools like Kubeflow and stuff like that, but I'll go here to one tool called Elira. I think originated from IBM or something, but here is the documentation. It's called Elira, in case you wonder, and this is a GitHub repo. So you can, it's just a group of extensions on top of Jupyter Lab, okay? So let's assume that we have 2 notebooks here, and actually it has very good Git integration. You can, this is my GitHub repo itself, and then I can go pull from remote and stuff like that, and you can get. I think there will be some changes because I put some stuff this morning. Okay, cool. And then you can have a look here. For example, if you wonder on the changes, oops, or history, you'll find, okay, yeah, you have all the magic from Git. You can do all your stuff here from a single environment. You don't need to jump between tools here and there. But what I'll show you now is like what the divide and conquer idea. Let's think about, okay, most of my talk was about big data and counting things and stuff. But let's switch to something similar to what we have seen this morning, which is about classification and plain AI and machine learning. And one of the, what they call it, the hello world types of machine learning applications is iris database or iris dataset, similar to stuff like MNest and so on. So it's about classifying the species of a certain flower. All right. So we pulled the repo, which contains two notebooks. I can run the whole notebook here, so you can divide your work. So where is that? This notebook maybe will be about pulling data and doing some sort of exploratory data analysis. So I'm pulling some data from a remote location, could be your own, I don't know, network file share or whatever, and then showing some data here, displaying some set of like statistics or whatever, and then doing some exploratory data analysis to understand more about your data. You can have another notebook about, okay, I'll take this data which has been downloaded locally here, and then do the train test split, use a library like scikit-learn or whatever library you prefer, do the machine learning or decision tree training, very similar stuff like what we have seen with Machine Learning Studio or the designer, but this time written as a plain Python code. All right, and then I run this one. Okay, run it. Okay, cool. We got a result here, but let's assume that this kind of two notebooks were prepared by a colleague of mine. And okay, looks good, everything is fine, as if I'm just reviewing a branch or PR from him. But I think there is like what it can be improved. So let's go here, for example, and change the depth of decision tree or max depth parameter to 4, and see what kind of performance or accuracy you can get. So I'll run this one once again. Okay, increased from, I think it was 91 to 95, which is quite good. Cool. So I can maybe save this one and share it with him or create a new commit or whatever and give him some feedback. But the idea, if you'd like to really test what are the deltas, what has changed, it could be too many changes implemented in the file or the notebook, you can switch to your Git node here, switch to changes, hit refresh. It can tell you like what notebooks have been modified. I can double click notebook number 2, sorry, and click def. If it takes a minute or so, close this one, right click def. No, it doesn't show for some reason. I'll open it and then maybe def once again. Anyway, seems something was going wrong, but eventually, if I had a screenshot, you'll see that the def experience is pretty good, and the deltas will be around this value, which has been changed from 2 to 4, and this value, which is an outcome of the cell. So eventually, we'll have a very good def experience. Maybe this one will work. No, yes, I don't know, but it seems that I need. Yeah, it's the first time I did this kind of demo like 2 or 3 times before, and yeah, unlucky today, but all good. But I think you get the idea. You will find very good local development experience here, including all the expected stuff from Git integration and source control and so on. And eventually, you have also the option to go and create a pipeline so that you can have one notebook doing a simple task and another notebook doing another task, and then you can connect them together and run them locally or run them on a cloud environment. So this kind of investment in tooling will save you lots of time. And if you are interested in similar tooling for Spark, not for plain like what data science or machine learning, there is another library called Spark Magic, which is virtually doing a very similar thing and working on top of another application called Levy. All right. So that's it. I think I've talked like what, I don't know, 5 or 10 minutes more, maybe, I don't know. So I think this agenda you have talked just quickly around data storage and file systems and how to balance your applications and how to do proper QA and governance, and finally how to pick good tools that will help you and make your life easy. So eventually, a combination of such things will allow you to have efficient big data applications and pipelines, and eventually can deliver faster, because it's not about having cool tech or whatever. It's more about value. It's more about customers. So yeah, using this kind of ideas or tips or whatever might help you with your journey with big data. And I leave the link for this kind of scripts and demos in the chat shortly. And thank you so much, and happy to listen to your questions. And sorry for the extra time I took.
Hey, Jose, thank you for that presentation. I really appreciate it. Thank you for getting involved, actually, one more year. As per questions, actually, I have a question for you. So I've seen in your presentation, actually, that you've been using Apache Spark pretty much for everything. Why should people look at Apache Spark and not any other big data clusters, for example?
Could be many reasons, actually. Some of them could be maybe bias or personal preference, but the big selling point for Apache Spark is that it's open source. It can run everywhere, so you are not kind of linked to a certain vendor or cloud provider. So if you have your code and jobs or whatever implemented in Apache Spark, you can take it from Azure and deploy it with AWS easily. It should work. Plus, most of, or maybe at least Microsoft itself, the latest inventions and stuff like what I think Synapse Analytics, they have two variations of the tool itself. One of them is just to use plain SQL, if you are just happy to just use high-level abstractions like SQL, and the other option is to give you a pointer to a Spark underlying environment. Okay, so you can just write your Synapse Analytics jobs in Spark. Okay, because sometimes your jobs might be a little bit more sophisticated and cannot be done in SQL by itself. You might need to reference some special libraries or some custom logic that cannot be done using SQL. So yeah, Spark is pretty amazing, plus the very big community around Spark itself.
That's a good point, because I was about to say actually that when you think about Azure Databricks, or you think about Azure Synapse Analytics, other platforms in Google Cloud or Amazon Web Services, they have actually they have built like wrappers around Apache Spark.
Yeah,
good point.
Yeah, but other than the tooling itself, it's more about also whatever tool you use. As you have seen here, some of the ideas were around pretty basic ideas, like you might need to know if what the data type of float will be stored as 4 bytes and the data type of double is 8 bytes, and do you really need the accuracy of double, or is it good for you to proceed with the float and stuff like that? So regardless of the tool, I mean, whether you use if you use Spark for 2 or 3 years or whatever, and then transition to some other tool, Synapse Analytics or AWS or Google or whatever, most of the learnings you have done using Spark will be also applicable over there.
That's an amazing point. Okay, thanks a lot for getting involved one more year. What's the best way for people to contact you if they have any questions?
I think, my Twitter handle over there, and can also reach me on LinkedIn. My name is pretty unique, so you can find it easily. So yeah, I mean, and then we can take it from there. Yeah, I'm pretty happy to have a chat with anyone interested.
Awesome. Take care. So next up, we'll have the closing and prices. This is a spelling mistake in prices there. Okay, but take care, Josie. Amazing presentation. Looking forward to have you next year as well. Bye.
Thank you so much, David, and have a good day, everyone.